Now we'll start the next chapter, that is polymers and polymerization. The next chapter is polymers and polymerization, so to say. So what are polymers? What do you understand by the term polymers? A polymer is a large molecule of very high molecular masses formed by the repeated combination of one or more type of monomers. We can say that is known as polymers. That is, polymer is a large molecule, is a macromolecule of very high molecular mass formed by the repeated combination, repeatedly, when the same monomers, alright, they also combine and they give rise to what you can say, that is polymers, or different type of monomers also they combine and they give rise to monomers, polymers, we can say that. Alright, so we can also say a polymer is a large molecule of very high molecular mass formed by the repeated combination of very large number of one or more type of small molecules. That also we can say monomers are also called as small molecules. Alright, mono means single. Alright. Now, the process by which polymers combine together and they form polymers, the process by which the monomers combine together and they form polymers is known as what? Polymerization. Alright, the process by which the monomers combine together to form polymer is called as polymerization. We can say that. That process is known as polymerization. Now, the structural unit which on repetition gives the entire chain of polymer molecule. Alright, the entire chain. For example, you get a polyethylene or polypropylene or polyvinyl chloride, which is called as PVC. That's the entire chain of polymer molecule. We can say that is called the repeat unit of the polymer. Alright, the number of times a particular unit is repeated, the number of times a particular small molecules is repeated, the number of times a monomer is repeated is called as a repeat unit of the polymer. It is known as a repeat unit of the polymer, we can say that, which gives rise to an entire chain of what you can say the polymers, we can say that. Clear? Now next is monomer is the building unit of polymer. The small units, like our body is made up of the small cells, that's a small unit. Similarly, the monomer is nothing but the small unit of a polymer. We can say that. Always remember that. Now, all types of organic molecule, what you can say, cannot act as a monomer. It's not that any, what you can say, monomer will take it. We will give some conditions and it will give rise to a polymer. No. No, it is not in that way. So, all types of organic molecules cannot act as monomers. We can say that. An organic molecule acts as monomer only when it's possess at least two reactive sites or the bonding site. That's a very important point. A particular molecule, an organic molecule, can act as a monomer which has got a reactive site, a particular bonding site. Then only it will act as a, what you can say, that is monomers. For example, CH2 double bond CH2. Double bond is there, na? Double bond is there. For example, if I say CH3 single bond CH3. Now CH3 single bond CH3 is not a monomer because we don't have any reactive site here in it. But CH2 double bond CH2, we have got a reactive site. We have got a bonding site here. Double bond is being present. Alright, like HC triple bond CH. Again I repeat, triple bond. So triple bond is a bonding site. Is the reactive site presented. What you can say, the monomers. So any organic molecule cannot act as a monomers. You can note this particular point, very important. Any organic molecule cannot act as. If it has got a bonding site, if it has got a reactive site, then only it acts as a monomer. We can say that. That you need to understand it. For example, I said you ethene can act as a monomer. Acetylene can act as, that is ethine can act as a monomers, but not ethane, because ethane, it does not have any reactive site. You know, ethane comes under alkanes. Alkanes are, what is that? Saturated hydrocarbons. Already it is fully satisfied. Alright, why it is going to react? For that purpose, you know that you have already studied. I don't want to go in details about it. That is, it is, as it is saturated, it undergoes substitution reaction, isn't it? And as these are unsaturated, they undergo addition reactions. Aldehydes, ketones, they have got a reactive sites, we can say that. Alcohols, they have got a reactive site, we can say that. Clear? So hence they can act as a monomer. So the number of bonding sites represent I'm saying the number of bonding sites present in a monomer is referred to as the functionality of the monomer, as of a polymer. The number of bonding sites, the number of reactive sites which is present in a monomer is called as the functionality of a particular, what you can say, monomer, which gives rise to a polymer, is known as the functionality. How many reactive sites are there, how many bonding sites are there, that is called as the functionality. If it is 2, we can say that minimum the 2 should be there, then only the chain can be formed, we can say that, because chain is formed in this particular direction, the chain can be added, as well as in the opposite direction of the chain can be added. And I'm going to show you now. I'm going to show you. So at least the 2 bonding sites should be there. For example, as I'm saying you, like HC double bond, that is CH2, in this way, HC double bond, then CH, then CH, CH2, or I can say CH2 double bond CH2. Now it has got 2 bonding sites. How you know? See, that is HC, here CH, here CH, and this double bond, it forms one bonding site, and this double bond, it forms another bonding site. So you can see 2 bonding sites are being present here. These are the 2 bonding sites. These are the 2 bonding sites. Got it? These are the 2 bonding sites. You can say minimum 2 should be there. In this way, that is the ethylene glycol. Got it? Is a functional monomer because it has got 2 OH group present in it. Got it? It has got 2 OH group present in it. We can say that. Clear? It can easily combine with COH group to form ester linkages. You know, alcohol reacts with acids to form what? Esters. The process is called as what? Esterification. We can say that. So in this way, that is ethylene glycol. Ethylene glycol, what is the formula? That is CH2OH, single bond, CH2OH. So it has got 2 bonding sites because of the presence of 2 OH group. So it reacts with the carboxylic acid group, that is COH, to form ester linkages. Later on you will be studying, which is known as polyester. Polyester. Together we call it as polyester. Alright, we can say that. Clear? Now, for that particular purpose, you can note it down, this particular point, that monofunctional molecules are unable to develop polymerization. I said, you know, ethene, ethyl alcohol, they are the monofunctional molecule. They do not undergo polymerization, but difunctional, 2 OH group, 2 bonding sites. Here also 2 bonding sites, minimum. This is just an example I'm giving you. It may be so many, we can have it. Alright, so monofunctional molecule are unable to undergo polymerization. They do not undergo polymerization, having one, that is, single functional group present in it. Got it? Bifunctional polymers form only linear or straight chain polymers. Note it, it's very important. Bifunctional polymers, got it, forms only linear or straight chain polymers. This is a bifunctional. This is a bifunctional. It is going to form linear or straight chain polymers. We can say that. Got it? Now, in case of trifunctional or polyfunctional, that is what you can say monomers, the polymers formed consist of 3 functional network. If you are having a trifunctional group, then it is going to form what you can say, due to the presence of 3 functional group, it is going to form a network structure, a 3-dimensional network structure. When you are having a 2 functional group, then it will be added in this way. The chain is going to grow in this particular manner. It is going to grow in this way. That means the chain is going to grow linearly. It is going to grow linearly. We can say that. The chain is going to grow either in this way or this one, linearly. But if you have got at least 3 functional sites you are having, that is 3 bonding sites you are having, then what if I say, let us say this is a monomer, it is having 3 bonding sites. This is a monomer, it is having a 3 bonding sites. Let me rub it this one, that will be easy for you to understand. So it will grow in this way, it will grow in this way, as well as it will grow in this way. So it will give rise to what? Give rise to what? 3-dimensional structure, because here one monomer can be added, here another monomer can be added, here another monomer can be added, got it? And here also the monomer can be added. Here also the monomer can be added. We can say that. Again, this monomer can be added in this way, got it? This way, as well as this way it can be added. So what you find is ultimately it forms a 3-dimensional network structure. You can see it forms a 3-dimensional. Still we can add it. Some more monomers we can add it here. Still we can add it. So it forms a 3-dimensional network structure in this way, having more than 2 functional groups, that is called as polyfunctional sites are there. Got it? If it has got 3 bonding sites, if it has got a polyfunctional bonding sites, more than 2, if 2, then the chain is going to grow linearly. Got it? You will be having linear polymers. But if it has got more than 2 bonding sites, more than reactive sites, got it? Then the chain is not only going to grow linearly, but also it is going to grow network. So it will form a network structure. You can see a 3-dimensional structure is going to form in this particular manner, we can say that. So such polymers, they possess high strength, high heat resistance, and are quite hard and tough. Alright, these polymers are having high strength, high heat resistance, and they are quite hard and they are quite tough. This particular polymers, we can say that. Got it? Clear? In this way, the linear molecular polymers, what you find is that they have strong covalent bonds. The primary bonds, they have got a strong covalent bond, and whereas the different chains are held together by weak van der Waals forces. Alright, the different chains, they are held together by weak van der Waals forces. In the presence of weak van der Waals forces, there is no restriction on the movement of these monomers. That is the movement of one chain upon the other. There is no restriction. One chain can easily move over the other chain. So it is being placed in this manner, linearly, one upon the other, in this way. In this way, it is being placed linearly. Alright, and these chains are held together by weak van der Waals forces. As a result, they can easily move one upon the other. This is about the linear polymers, and this is about the cross-linked on the network polymers as said. So you can understand that how the linear polymers is being formed and how a network polymers is being formed, depending upon the number of bonding sites. Alright, depending upon the number of active sites, reactive sites, we can say that. So the number of repeating units present in a polymer is referred to as the degree of polymerization. Alright, it is asked generally, what is the degree of polymerization? So number of repeating units present in a polymer is referred to as the degree of polymerization. We can say that. Again, I repeat, the number of repeating units present in a polymer is referred to as the degree of polymerization of the polymer. We can say that. Now you understood what is a polymer, how a polymer is being formed, got it? How a linear polymer is being formed, how the chain grows linearly, how it grows 3-dimensionally, got it? If it grows linearly, what is its properties, what is its characteristics? If it grows 3-dimensionally, what is its characteristics and properties? You have understood. Now, based upon that, we will be coming to the classification of the polymers, different types of polymers. So, first of all, the classification on the basis of origin. Alright, on the basis of origin, we will understand the classification. So, polymers are basically divided into natural polymers and artificial polymers or synthetic polymers. We can say that. Basically, it's divided into natural polymers. Got it? You may write it down. Natural polymers and synthetic polymers or artificial polymers also we can say. We have also got semi-synthetic polymers. Semi-synthetic means naturally as well as artificially, both are involved in it. Got it? That's said to be semi-synthetic. We will come to it later on. Now, natural polymers, the polymers which occur in the nature are called as natural polymers. Very simple it is. Got it? For example, starch, cellulose, then proteins, nucleic acids, natural rubber, etc. They come under natural polymers. We can say that. Starch. What is starch? Already I have said you in biomolecules. I have told you what is starch. Once again, let me repeat. That is, it's a polymer of alpha D glucose. D, capital D, D type. So alpha D glucose, in a starch molecule, hundreds of alpha D glucose molecule are joined together through a particular type of linkage called glycosidic linkages. Alright, that is called as a starch. Hundreds of, what you can say, molecules are joined together through a particular type of linkages. Alright, that is called glycosidic linkages. What molecules? That is alpha D glucose molecules, and it forms starch. We can say that. Next, it's the main food reserve of the plant. Starch is the. Now, next is cellulose. It's a polymer of beta D glucose. That was alpha D glucose. This is beta D glucose. That is cellulose, and consists of hundreds of beta D glucose units joined together through same thing, beta glycosidic linkages. Alright, that was glycosidic linkages, rather alpha glycosidic linkages in case of starch, but in case of what you can say in cellulose, it is beta glycosidic linkages. We can say that it is a main structural units of material of plants. We can say that. Now next is proteins. Proteins are polypeptides and are formed by the polymerization of amino acids. Proteins, they are the polypeptides and formed by the, that is polymerization of the amino acids. When the amino acids, here the amino acids are the monomers. When the amino acids undergoes polymerization, that is NH2CH2COH, that is the general formula or the formula of amino acids, we can say that. They form long chain of polymers and they can also be cross-linked. They can also be networked, we can say that. Got it? So a protein molecule is composed of 20 to 1000 amino acids, we can say that, joined together in a long chain or in a cross-linked chain. Got it? We can say that. Now nucleic acids are the polymers of various nucleotides and consist of base sugar phosphate. Got it? Units. So what I said, nucleic acids are the polymers of various nucleotides and consist of base sugar phosphate units. We can say that. Clear? They are present in chromosomes of cell nuclei, we can say, and control the hereditary characters. We know that. Now next is rubber. Natural rubber is obtained from the rubber tree, is a polymer of 2-methyl, that is buta-1,3-diene. 2-methyl, not sorry, 3-methyl I said, 2-methyl buta-1,3-diene. Got it? It's obtained from the rubber tree, which is commonly known as isoprene, we can say that. And it undergoes polymerization to form polyisoprene, which is called as rubber, we can say that. Clear? That is it is obtained from the latex, the milky juice of the plants in the bark of the rubber trees, isn't it? That is called isoprene. What is that isoprene? Is 2-methyl buta-1,3-diene. 2-methyl buta-1,3-diene when undergoes polymerization, then what it forms? It forms, that is nothing but rubber. That is natural rubber. 2-methyl buta-1,3-diene. We can write it and see. Buta-1,3. So it is 1,3 and 2-methyl 1,2. Let us say here the methyl. So n number of 2-methyl, this is your isoprene, undergoes polymerization. It undergoes polymerization, we can say, to form polyisoprene. In case of polyisoprene, now here I'll put the hydrogen atom, of course, CH2, then here of course it is satisfied and here it will be CH2. So what you'll find is that it is being added chain wise. No? This is your active site. This one is active site, this particular one. So here one chain will be added. So it will be CH, then C, then CH3, then CH, then CH, whole N. This is known as, so here I have kept the chain here. There is, so some more isoprene will be added. Here also some more isoprene will be added and it will form a long chain which is called as polyisoprene, we can say that. Now we need to balance it. We'll balance it. Not balanced. The carbon atom is not balanced. You can see it here. Here 3 bonds. Here also carbon is how many bonds? It is nothing but 1, 2, 3 bonds. So it is CH2. Now here it will be your CH double bond. You see now it is balanced. You can see now it is balanced. Now it is again CH2. It is this. Now just count it. Carbon is having how many? That is 2 bonds, 2 hydrogen and 2 bonds. Correct. Carbon is having 1 hydrogen and 3 bonds. Correct. This carbon 1, 2, 3, 4 bonds. Correct. And this carbon also it is 3 and 2 bonds, 2 hydrogen and 2 bonds. Okay. In this way we do it. Very simple it is. First I gave the bonds, you can see. Then after that I balance the hydrogen atom. Done. Finished. So in this way it forms, that is nothing but polyisoprene, which is nothing but known as your rubber, we can say that. Now next, these are all coming under natural polymers, we can say that. It comes under natural polymers. Then we are coming the semi-synthetic polymers. These are the mostly derived from naturally occurring polymers by chemical modification. For example, cellulose diacetate. Alright, what I said you, these are mostly derived from naturally occurring polymers by chemical process, by chemical modification. Example, that is cellulose diacetate. Cellulose diacetate is used in making threads and materials for films, for glasses, etc. Gun cotton, then vulcanized rubber, they are also coming under semi-synthetic polymers, we can say that. And synthetic polymers, then after that, the polymers which are synthesized in the laboratory entirely. Their natural process was involved. Here it is completely synthesized in the laboratory, is called as synthetic polymers or artificial polymers. Example, your PVC, bakelite, nylon, this polyester, then polythene, we can say that polypropylene, they are coming under that is synthetic polymers, so to say. Now this is the classification of polymers we did on the basis of origin. Now we'll see the classification of polymers on the basis of structure. So there are three types of polymers there. Linear polymers, branch chain polymers and cross-linked polymers. Alright, what I said? Linear, branch chain and cross-linked. So first we'll come to the linear polymers. This is your linear polymers. This one is a linear. Just now I was saying you. This is your linear polymer. We can say that. Now this is your branched polymer. Branched. We can say that. Branched polymer. This one is. And this is your cross-linked. A combination of branched and linear. We can say that. A combination of branched and linear polymer. This is your cross-linked, or I should say network polymer. Also it is being called as. Cross-linked polymer or network polymer is also said to be as. Clear? So in this way, what is linear polymers? Linear polymers are polymers in which the constituent monomeric units are joined together to form long straight chains are called linear polymers. Long straight chains are called linear polymers, we can say that, or straight chain polymers. Due to close packing, so when it is having a long close chains, then so it will be packed closely because it is symmetrical. We can say that all the chains are similar. All the chains are equidistant from one another. We can say that. So hence they are packed very closely, very tightly. We can say that. Due to close packing of the polymeric chains, linear polymers, they have got high density, they have got high tensile strength, they have got high melting point. We can say that. High density, high tensile strength. Why it is high density? Because number of polymeric chains, what you can say, are being present in a small unit, meaning small volume. So definitely volume is less, means density will be more. So high density, high tensile strength and high melting point. High density polythene is an example of linear polymer. HDP, high density polythene. We have also got low density polythene, LDP. So high density polythene is an example of a linear polymer, so to say, HDP. Now branch chain polymer, the polymers which consist of side chains of monomer units. You can see side chain of monomer units and the branching is being present in it. Alright, so are called branch chain polymers. Attached to the main chain, we have got branches. Again I repeat, the polymers which consist of side chains, that is of monomer units, attached to the main chain or linear polymer is called as the branched chain polymer. See, in the main chain we have got branching. See, in the main chain we have got this branching. This is called as a branch chain polymers. Now due to what you can say irregularly, the branches are not regular, they are irregularly packed. They are not closely packed, they are not tightly packed, they are not symmetrical in nature, they are unsymmetrical. Alright, they are irregularly packed, we can say that. Due to the presence of branches, they have got lower density because volume will be more. So density will be less. So lower melting point and lower tensile strength. So you can say the linear and the branch chain polymers, they are just opposite in nature. Opposite, completely opposite in nature, we can say that. So they have got low tensile strength, they have got low melting point, they have got low density, we can say that, as compared to linear polymers. So low density polythene, already I said you, LDP is an example of what you can say branched polymer. We can say that. Next, cross-linked polymers, the polymers in which the adjacent polymeric chains are linked together through side chains. Alright, to form a three-dimensional network, you can see the adjacent polymeric chains are joined together by side chains to form a three-dimensional network. A three-dimensional network, we can say that. So cross-linked polymers, due to this reason, they are hard, they are rigid, they are brittle in nature. Example is formaldehyde, melamine, we can say that, bakelite, we can say that, we can say urea formaldehyde resin, we can say that. They come under cross-linked polymers, so to say, or that is your branched polymers, so to say. Now, what is the effect of chain length? If the chain will be longer, if the chain will be shorter, what will happen? Alright, so we'll see the classification of polymer on the effect of chain length and cross-linking. That is, rather I should say, I am talking about physical properties. Alright, clear, of polymers. Clear? So, when the polymeric chains of a polymers are short, it is smaller, it is shorter. The polymer has got a low average molecular mass and low degree of polymerization, definitely. If number of chains is less, if number of monomers is less, if the chain is shorter, then it has got a low degree of polymerization. We can say that. Clear? So, due to which the polymer is soft and gummy, got it, and hardly possess the properties characteristics of a polymer. It is soft, gummy means sticky, we can say that. Clear? So, in this way, on the other hand, the polymeric chains, if it is long, if it has got a long polymerization, long polymeric chains and have got high degree of polymerization, we can say that. So, if average value molecular mass is also more, such a polymer is tough and heat resistant. If it has low degree of polymerization, the polymer is soft and gummy. We can say that. It is sticky. But if it has got high degree of polymerization, means the chain length is longer, having large average molecular mass, higher molecular masses, then the polymer is tough and heat resistant. We can say that. So you got it, the difference between the effect of chain length of two types of polymers. Now, if there is effect of cross-linking, what is the effect of cross-linking? When the cross-linking is present, you can see here the cross-linking, the network is being present. What is the effect? Due to this reason, it will be having low density, low melting point and low tensile strength. It will be having. Alright, due to the cross-linking. Alright, so the polymer is tough and strong. On the other hand, that is linear polymer without cross-linking. I have already said you, it has got high density, high tensile strength and high melting point. Alright, with the cross-linking, it will be low melting point and low tensile strength. Alright, the linear polymer which is having, and it is tough and strong. Alright, and this having without the cross-linking, the polymers, we can say that no cross-linking is there. Then high density, it will be having high melting point, it will be having high tensile strength. All those things will be higher, we can say that. Now, next is coming to the type of monomers attached to it. That is classification of polymers on the basis of the monomers or the structural units attached to it. That we'll see in the next video. Thank you.